this video, we will learn about Gauss's law. Here I presume that you have introduction to the concept of electric field, electric lines of forces of field lines, and electric flux. Now, Gauss's law relates electric field to the charge distribution which has produced this field. We already know how to calculate electric field using Coulomb's law. So why do we need yet another law? The answer is that there are certain situations where Gauss's law gives us a much easier way to calculate electric fields than directly using Coulomb's law. And you will notice this when we will discuss about applications of Gauss's law. So we now know that Gauss's law deals with the electrostatic field, and concept of electric field lines is central concept for studying Gauss's law. Gauss's law is based on the fact that flux through any closed surface is the measure of total amount of electric charge inside the surface, and any charge outside the surface would not contribute to the total flux. Now we know that electric flux through any closed surface S is phi is equals to integral E dot dA, and it is the number of field lines passing through the surface S. Now Gauss's law states that electric flux through any surface enclosing charge is equal to Q upon epsilon naught, where Q is the net charge enclosed by the surface. Now mathematically, Gauss's law is given as integral E dot dA is equals to Q upon epsilon naught, where this Q is net charge enclosed by the surface, and E is the total electric field at each point on the surface under consideration. Now, as said earlier, it is the net charge enclosed in the surface that is counted in Gauss's law. But the total flux of electric field depends also on the surface chosen, not merely on the charge enclosed. So if you have information about distribution of electric charge inside the surface, you can find electric flux through the surface using Gauss's law. Again, if you have information about electric field or regarding electric flux through any closed surface, then total electric charge enclosed by that surface can easily be calculated using Gauss's law. Now, surface on which we apply Gauss's law is known as Gaussian surface, which need not be a real surface. A Gaussian surface can be an imaginary or geometrical surface which might be empty space, or it could be a partially or fully embedded in a solid body. Now again consider the mathematical statement of Gauss's law, which is E dot dA is equals to charge enclosed upon epsilon naught. Now in the left hand side of this equation, E dot dA is a scalar product of two vectors E and the area vector dA. This area vector dA is defined as the vector of magnitude modulus dA, and its direction is the outward normal at the area element dA. So dA is equals to n cap dA, where this n cap is the unit vector along outward normal to dA. So E dot dA is equals to modulus E cos theta dA, where this theta is the angle between normal to the surface element dA and radial line from charge Q as shown in this figure. Now from this we can draw two conclusions. First one is, if both electric field E and surface area at all points are perpendicular to each other and electric field has same magnitude at all points of the surface, then this vector E has same direction as that of area vector. So since E is perpendicular to the surface, E dot dA is equals to EA. And the second one is, if E is parallel to the surface, then E dot dA would be equal to 0. So this is the introduction about Gauss's law, and for more information like notes and study material on Gauss's law, you can visit our website physicscatalyst.com.